Okay, so let's pick up where we left off, going over the solutions for a simple harmonic motion set 2. We're going to do number 6. Okay, so we have a standard mass on a horizontal spring. In this case, we're told the spring constant, and we are told that it has an initial velocity of negative 2.96. That's going to be important. So I've drawn a crude picture up here. So here's the block, and at time 0, that initial velocity is going to be to the left. In other words, in a negative direction. So that's going to guide us in coming up with the proper trig functions. But before we get to that, we need to establish some important aspects of this motion, namely the period and frequency, because that's going to show up in the sine or cosine part, and then the amplitude, because the amplitude would go out in front when we're trying to understand position. So this is stuff we've done a lot. So the equation for period, again, is 2 pi radical m over k. Okay, so put in the numbers, everything is given, pretty straightforward, and we get 0.49 seconds. All right, frequency is the reciprocal of period, so 1 over 4.49 is essentially 2, and 2 cycles per second. All right, amplitude. So nothing in here is given amplitude, and what we want you to understand conceptually is amplitude is tied in with the energy, potential energy. So at the beginning, it has, at time 0, it has all kinetic, and then it's going to compress a maximum amount. So in other words, that kinetic, when it reaches 0, is going to be all in elastic potential. So once again, we have 1/2 mv squared equals 1/2 k, and since we're looking at the maximum displacement, that's where our amplitude comes in. So not just a generic x squared, but an a squared. So put in the numbers, solve for a, and we get 0.23 meters. Okay, so that's a, and that's going to come up later. All right, now we want to come up with equations for position, velocity, and acceleration as a function of time. And before we can jump right in that, let me remind you of a few things. In your reference tables, the generic equation for position as a function of time is essentially a cosine, right? And I'm not sure exactly, so omega t or t over the period, but this is the generic. We can't necessarily assume this is what's going to be the case. We're going to look at the initial conditions, and we know what the initial conditions given are as follows. At t equals 0, we know that v, okay, is negative 2.96, and that's at its maximum. We know it's got to slow down for any position to the left or right of that initial one, and it's moving in a negative direction. Okay, so if I want to plot, I'm going to draw a crude graph first before I develop the equation because it helps determine whether I want sine or cosine. So I'm just going to reason this out. So this is x, and at time 0, we know it's at position 0. That's given. And then we know it's moving in a negative direction. So at some point time later, it's going to be down here at a maximum displacement, then back to 0. I don't need much more to figure out that this is the shape of the graph, and that's a negative sine graph. So we're going to still use this form, but instead of cosine, we're going to have a negative sine. So the generic equation then, x is negative for the negative sine, amplitude sine, okay, of omega t. All right, so we know what amplitude is. We found it right here. We don't have omega, but we can get it easily from frequency. So we can say omega is 2 pi f, right? F is 2, 2 times 2 is 4, so it's essentially 4 pi. And I'm going to leave it like that, even though 4 pi is equivalent to about 12.8. You can have that as well. So this equation then becomes x equals negative 0.23 sine of 4 pi t. Or again, instead of 4 pi, I could have 12.8. Now I believe in the answers, it might have had this as a positive, and I believe that's because when we originally did this was a positive value, and it was changed over the years, so the answers don't necessarily reflect that. All right, so what's going on with velocity? Well, again, we can take the same approach in terms of figuring out which trig function we want to use. We know it's the slope of this, so we could look at the slope, or we can reason it out based on given information. So at the beginning, it's moving in a negative direction. Negative, what do we say, 2.96. And then it's going to slow down to 0 when it gets to maximum amplitude, and then gain speed in the opposite direction. So we're going to have a graph that looks like that. That's a negative cosine function. So we can say V, right, the generic form is V is equal to V max. All right, in this case, negative cosine omega t. So now we can substitute in the numbers. So that is going to be negative of a negative. So it's going to be 2.96 times the cosine of 4 pi times time. Okay, pretty straightforward. And then acceleration. Okay, that again is the slope of this graph, but what's in terms of reasoning that out? And this is a little bit more difficult. All right, at time 0, the position is 0. In other words, it hasn't been stretched, so there's no force on it, at least from the spring. We're not worried about the force that came from the hammer blow, because once that event is over, then that's what we're talking about. So there's no initial acceleration. And then we know it's moving in a negative direction. And an important thing you want to remember conceptually, if it's moving in a negative direction, its velocity is negative, okay, then its acceleration has to be positive. It's always, acceleration and velocity are always out of phase with one another. So we're going to have a positive initial acceleration, and then a maximum when it comes to a stop. And then when it rebounds, if you will, it's going to go to 0. So we again have that recognizes a sign. So the equation, a generic equation now for acceleration, is basically a max, whatever the maximum acceleration. Remember, the maximum acceleration can be derived from Hooke's law, right? In other words, F equals kx. In this case, x is a when we're at maximum amplitude. Boy, let me erase that. That's awful. All right, so F is equal to K. We want the maximum, so that's going to be at the maximum displacement. And of course, that equals ma, the second law. So the maximum acceleration is always going to be K times A all over m. So I'm going to put out here the maximum acceleration, K times A all over m. And this is a sine omega t. So if I plug in the numbers for k, a, and m, you can do that on your own. You should get a positive 37.8 and then sine of 4 pi t. Okay. And then we can ask, what's the total energy of the system? Well, the total energy of the system is either the sum of the potential and kinetic, or the sum of just the kinetic when it's at a maximum, or the sum of the potential when it's at a maximum. So we know that V max is negative 2.96, so we can simply figure out the total energy by the kinetic energy max, which is 1/2 mv squared, or V max squared. And plug in the numbers, and we should get about 3.31 joules. Okay, so ask any questions on Schoology. Hopefully this makes sense.